In this lecture, we are going to see ARMA random processes. Okay, so what is an ARMA random process? An ARMA random process, when we expand, is auto-regressive moving average. So this is nothing but auto-regressive moving average. Right. Now, how do we characterize this function or how do we go about this? We always have an input to a system, then we have a relative output from the system. So if my W of n represents input to a linear time invariant means it does not change with time. Linear time invariant causal system, and x of n is the output, then the input output relationship can be written as x of n equal to minus sigma k equal to 1 to p ak x of n minus k plus sigma k equal to 0 to q bk w of n minus k, where our p is always greater than q. Let us take this equation to be equation number 1. The equation is defined, this equation is defined for all n greater than or equal to 0. If W of n is a white sequence, if W of n is a white sequence with its expectation E of W of n equal to 0, that is 0 mean, and E of W of j into W of k equal to sigma squared delta jk for all j and k, the resulting process x of n is called an autoregressive. It is called an autoregressive moving average. Autoregressive moving average. In simple words, in abbreviation, an ARMA process. I suppose now you get a clear idea. If W of n represents input, x of n is the output, and x of n takes the form given in 1, and p is greater than q for all n greater than equal to 0, where the input W of n has a 0 mean and E of Wj into Wk equal to sigma squared delta Jk for all j and k, then x of n is called the autoregressive moving average, or the ARMA random process of order p comma q and is duly written as ARMA open bracket p comma q, indicating its order. Right. Now, if you watch very clearly, there are two terms in this equation number 1 corresponding to x of n. Suppose the first term becomes 0, that is, the negative term does not exist. Then this x of n over here is called a moving average process of order q, because this p portion vanishes. So it is just a moving order process of order q. Let us now write it separately. We are going to write the equation for moving average process of order q. So for this purpose, we are going to take our equation 1, consider equation number 1, and then for all aq equal to 0, ak equal to 0, where my k equal to 1 comma 2 comma etc up to p, the resulting random process I denoted as capital RP, okay, for simplicity. X of n is called moving average process of order q, is called a moving average process of order q. Now let us look into the equation of this process. It is denoted as MA of q. Right. How does this equation now look? Your first term becomes 0 in equation 1, giving you x of n equal to summation k equal to 0 to q bk w of n minus k. Right. Now we have to consider different cases and we will start characterizing this process slowly. So now what happens if bk equal to 0 in equation 1? That is the next concern. If bk equal to 0, we will get something known as the autoregressive process. Okay, so how do we define autoregressive process of order P? So when we have to define autoregressive process of order P, now we put bk0. If bk equal to 0 in equation number 1, see, this is our equation number 1. Now bk is 0, the positive term vanishes, that is the second term, and only the first term is in existence for us. Okay, so if bk equal to 0 for my k equal to 1 to q, then it is called then it is called an auto regressive process. Then it is called auto regressive process of order P. It is denoted as AR of P. How do you represent this? This is nothing but go to equation 1, put the second term 0. So x of n equal to minus summation. I will run k from 1 to p, and I will have ak x of n minus k plus, I will see, I should be very careful. I have taken k from 1 to q. So k equal to 0 will exist for me, giving me b naught into w of n. Okay, so this is how we define an auto regressive process. Now let us slowly move into explaining moving average process in depth. So we are first going to see moving average process of order q, which is denoted as ma of q. Okay, so how do we go about this? The governing equation for the moving average process we have already given you just in 2 3 slides before. So when I consider this, my equation is got from equation 1 by putting ak equal to 0. So my x of n will be summation k equal to 0 to q bk w of n minus k for all n greater than equal to 0. Now w of n here is white stationary process. This is a white stationary process with zero mean. So zero mean in other sense, our E of W of n equal to 0, and variance variance E of W squared of n. How variance turns out to be this term? The reason is E of W of n the whole square becomes 0. So only this term will exist to contribute to the variance sigma squared for all n greater than equal to 0. Okay, I recall my sigma squared is nothing but E of x squared minus I have E of x the whole square, and incidentally this term becomes 0 for us, leading to only existence of the first term, which is E of W squared of n equal to sigma squared. Okay, right. Next we move on to see the mean of the moving average process. So mean of moving average process q. What is this q? Q is nothing but order of the process. Okay, so let us now go on to see the mean. So I know that my E of x of n is mean. So let me first consider my x of n. What is going to be my x of n? X of n is this particular term minus summation 0 to p. So when I have to run for this, what happens here? This is autoregressive process. I am into my moving average process. So for my moving average process, it is going to be k equal to 0 to q bk w of n minus k. So let me rewrite my x of n. My x of n is going to be summation k equal to 0 to q bk w of n minus k for all n greater than or equal to 0. Right. Now let me take my expectation. E of x of n is nothing but summation. I will have k equal to 0 to q. Bk is going to be a number. So you pull the expectation inside E of w of n minus k. Now what I know? I know that mean E of whatever be this n minus k or n equal to 0. So this value E of x of n is now going to be equal to 0 for all n greater than or equal to 0. Next, once we have seen the first order moment mean, we move on to see the variance. Variance of moving average process. Variance of the moving average process of order q. Okay, right. Let me start. So my variance is nothing but we saw that the mean equal to 0. So you will only have the E of x squared term which is going to remain for us. So here this is nothing but E of, I will have x minus x bar the whole square. That's another representation for variance. So that gives me E of x of n minus my E of x of n the whole square for all n greater than equal to 0. Now here mean is 0, here mean equal to 0. Therefore my variance sigma x squared of n is nothing but I will have E of x squared of n, and this is nothing but my E of, I will have E of summation k equal to 0 to q bk w of n minus k, this whole term whole power 2. Now I can rewrite this and split this. How am I going to split this term? This could be rewritten as I will have E of, let me write my first term, I will have E of summation k equal to 0 to q bk w of n minus k into summation j equal to 0 to q bj w of n minus j. Now this could be rewritten as, let me continue with my proof. So this could be rewritten as I rewrite sigma x squared, that is my variance left hand side, just to remember what we are following up with. So this is equal to summation, I will have k running from 0 to q, I will also have my j running from 0 to q, I will have bk bj, I will have e of w of n minus k, e of w of n minus k into w of n minus j. I will be left with this expression. Now what is this expression? This is nothing but equal to, I will have sigma square summation k equal to 0 to q of b k squared for all n greater than or equal to q. Now if my k is not equal to j, then I have to consider this expression E of w of n minus k into w of n minus j. This value, they are both independent. E of xy is E of x into E of y. So I will have E of w of n minus k into E of w of n minus j. In this aspect, this I already know that mean is 0, therefore this value becomes 0. So we end up with this particular term as our final answer for our variance. Next, suppose we have if 0 less than equal to n less than or equal to q, or rather sorry, strictly less than q, then how will the above result get modified? So this then leads to include only those terms, it leads to include only those terms w of n minus k and w of n minus j that have arguments that have arguments which are non-negative, that is greater than or equal to 0, and thus and is thus a function of n. Hence I will have my sigma x squared of n, in this case giving me sigma squared summation k equal to 0 to n b k squared for 0 less than or equal to n strictly less than q, right? So the variance is a function of n. So the variance is a function of n, and a part of the initial transient period until n reaches q, yielding a steady state after that. So you have both a transient state and a steady state, right? Having looked into the variance, we will go and have a view of how the autocorrelation function of this MAQ looks. What is MAQ? Moving average process of order Q. So autocorrelation autocorrelation function of the moving average Q. How do you represent an autocorrelation function? It is either represented as Rxx of t1 comma t2, where you consider a process x of t at two independent times, that is t1 and not two independent. You will consider it at time t1 and at time t2. Okay, so here in this case, for k comma j less than 0, now we will be representing autocorrelation as Rxx of j comma k equal to 0 for the moving average process of order q. In general, in general, this term Rxx of j comma k will depend on two time indices. It will depend on two time indices. Say here my t1 is the start time. Here I will have two time indices t1, say k, and t2, which is got by incrementing k by m. Okay, where both k and m are positive integers. Me using t1 t2 here simply because we feel very comfortable with this notation. Rxx of t1 comma t2 is nothing but e of x of t1 into x of t2, which is the standard notation which you would have been introduced to in your undergrad courses and especially in random process. Okay, so that is the reason why I use t1 and t2. Otherwise, from now on, we stick to k and k plus m. Right. So now I have e of x of k plus m into x of k. This value for us is now going to turn out to be e of summation I equal to 0 to q, summation I equal to 0 to q bk w of k plus m minus I into summation j equal to 0 to q bj w of k minus j for all k comma m being greater than or equal to 0. Now let k be greater than q. So let k be greater than q and let my 0 less than equal to m less than equal to q. With these conditions, I will find that the autocorrelation function Rxx of m plus k comma k is nothing but the expectation of I will have b naught w of k plus m plus b1 w of k plus m minus 1 plus etc. I will reach up to bq w of k plus m minus q. This whole thing, so let me use a different color for variation. So this whole thing into I will have b naught w of k b1 w of k minus 1 plus etc plus bq w of k minus q. These would be the terms inside this expectation. Only those with equal indices will give non-zero terms. Otherwise, all other terms you will split as some e of x into e of y. Mean is 0, so all the other terms will vanish. This leads to the result that my Rxx of k plus m comma k will now be equal to summation r equal to 0 to q minus m br into br plus m e of I will have w squared of k minus r. So this in other words is by notation sigma squared summation r equal to 0 to q minus m br br plus m. Here my m lies between 0 to q. Okay, so for m greater than q, for m greater than q, there are no overlaps. So what happens? This autocorrelation will tend to become 0. So r k plus 1 comma k equal to 0. That is, we are telling there is no term like e of x squared. All will be only comprising of mean, and we know mean equal to 0. Therefore, this is equal to 0. Clearly, we know that the autocorrelation function is independent of the start time. We are bothered only about Rxx in general of t1, t2. That means we are bothered only about a time slot tau where this tau runs from t1 to t2. This could be some say 5 minutes, 10 minutes and so on. So it could be from 5 to 5:05, or it could even be from 10 o'clock to 10:05, something like that. So it is only bothered about the interval here, the width between t1 and t2, that is represented as tau, and not on the starting time k. Okay, so it is a difference or the time difference of the function time of difference m where k is greater than q. Thus, after a time q, the mean is constant, that is, it is 0. Hence, the autocorrelation function is a function of time difference. Therefore, it is a WSS process. Since it is only time difference, it is a wide sense stationary process, or it is a WSS process. Thank you for your patience and kind listening. I think now you would have understood what is meant by an ARMA process, how an ARMA process gets split into two, that is, your moving average process and your autoregressive process. And in this video, we have seen in depth moving average process, its mean, its variance, and its autocorrelation function. Thank you.